Hi, everybody. I thought maybe even though today is a holiday, we could have a review for the looming exam number 3 this week. So I posted a document with some problems on the course website, so maybe you'll want to do some of those. And I have a selection of of problems here, not necessarily the same ones on that document, but maybe be worth going through anyway. Okay, so first of all, how about let's try some product prediction. And let's not spend too much time on this because this is probably the easiest part of the exam, and probably we'll want to focus on synthesis and mechanism. Okay. Okay, so let's try this product prediction problem. Draw the structure of the product or products. So what kind of reaction is this going to be? Are you thinking acyl substitution? Yes. I see a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. And so the thing that's not carbon and not hydrogen is going to break off, and it's going to take off as a leaving group. The conditions here are basic, right? It's not acidic conditions, it's basic conditions that KOH. So that this kind of reaction is called a saponification of an ester. Okay, so there's the carbonyl carbon that's bonded to something that's not carbon and not hydrogen. This bond is going to break, and that's going to take off as a leaving group. There's a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. That's going to take off, and that oxygen is going to function as a leaving group. And once again, here it is again. There's my acyl carbonyl bonded to something that's not carbon and not hydrogen. And so that's also going to function as a leaving. So these oxygens go away, and what takes its place? The nucleophile. The nucleophile here will be water, but look out, we're under acidic conditions. And one of the hallmarks of acyl substitution basic conditions, one of the hallmarks of acyl substitution under basic conditions is that frequently the acyl substitution ends, but the reaction does not end because there's a follow-up or sequel reaction. Okay, so what I would do here is put the nucleophile, which is water, minus the proton, right there. Put the nucleophile minus the proton. That's this guy down here. And over here, we would have another one just like it. Okay, and meanwhile, this oxygen, and this oxygen, they took off as leaving groups. And in a formal sense, they pick up the extra proton that water came in with. Okay, so we might be tempted to write this, but this would not be correct because we're under basic conditions. And that's a carboxylic acid. This proton is pretty acidic. That's a carboxylic acid. That's a carboxylic acid. So that instead of carboxylic acids as the product, because we're under basic conditions, all of these guys have to be changed to carboxylates. And you know, the people who grade your exams, they're pretty rough. So that if you were just wrote OH here, OH, OH, they'd probably mark it wrong because it's acyl substitution basic conditions. You have to watch out if the product is susceptible to an acid-base reaction as it is there. Okay, so how'd that go? Yes? Okay, let's try another one. First step, ethoxide in ethanol. Second step, methyl iodide. Third step, H3O plus. Okay, draw the structure of the problem. Oh, this chalk is killing me.
Kelly, can you read the text?
Okay.
So is this acyl substitution? Well, I see a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. But the leaving group, OET, will be the same as the incoming nucleophile, also OET. So acyl substitution is happening, but it doesn't lead to the creation of any new compound. So although it might look like, that first step might look like acyl substitution, that's what it
Yeah.
This is the line moment I go to.
so, unless you're speaking to me, can you please mute your mic? All right, so the an important thing when you're studying these reactions is recognition of starting materials, reaction conditions, and products. Who lives to the left of the arrow, who lives above the arrow, and who lives to the right of the arrow. Okay, so what I see here, this is my big clue. This is an ester, and the base here matches the esteratic portion of the ester. So I'm thinking some kind of enolization reaction, probably going to be a Claisen. Okay, so we're looking for something that can enolize in this first step. Okay, and so we're looking for an alpha proton. That's an alpha position. We could get enolization here. That's an alpha proton. We could get enolization there. That's an alpha proton. We could get enolization there. But after, in our imagination, we see those negative charges there. Now we have to wonder, well, what are they going to do? If we have a negative charge here, the most likely reaction would be an intramolecular reaction where this guy, this negative charge, this enolate is going to attack a carbonyl. But the only available carbonyl is 1, 2, 3, 4 bonds away, so that's not going to happen. A 4-membered ring has a lot of ring strain, and so that's not going to be likely. There's an alpha position here, and what is this alpha position going to do? It's going to attack a carbonyl, and the only available carbonyl is 4 atoms away once again, so that's not in the cards. There's an alpha position, and this guy is going to go after a carbonyl. 1, 2, 3, 4, 5, 6. Yep. Okay, so first step is the formation of the enolate. And that enolate is going to be over here. And then, so that's what we get at the end of, okay, so now this enolate attacks the carbonyl to make that 6-membered ring. was OET, CH2, carbonyl. This was my attacking nucleophile. That was my attacking nucleophile. There's my electrophile. There's my attacking nucleophile. There's my electrophile. Okay, so the enolate attacked the carbonyl. And now we have expulsion of this leaving group. To give us this. We're still in step one, believe it or not. Okay, this is acyl substitution, basic conditions, right? The attacking nucleophile attack the carbon that is bonded to something. It's not carbon, not hydrogen. The thing that's not carbon, not hydrogen went away. But as I said before, whenever we're looking at acyl substitution under basic conditions, is that there's nearly always a follow-up reaction to acyl substitution in base. And here, this guy has a bis alpha carbon. It's a carbon that is trapped between two carbonyls. The pKa of this proton here is about 10. That's a pretty strong base. So we're still in step one. This is not the product of step one. Now we have ethoxide coming in, ethanol coming out. What happened is the deprotonation of that bis alpha position, right? And so now that's the end of step one. So that's what we get at the end of step one. It's a Claisen, and we have to remember that frequently the Claisen is going to give a bis alpha. It's going to give a 1,3-dicarbonyl with a carbonyl trap, with a carbon trap between two carbonyls, and those are acidic. Under basic conditions, the proton will be removed. Okay, so that's at the end of step one. All right, now this is going to be an SN2 reaction. Iodide is a good leaving group. That's the nucleophile. So we'll have alkylation of the enolate. And that CH, that workup with acid is just getting rid of all of any residual base that remains. There's really no new chemistry there in step three. It's just getting rid of any ETO minus that might remain, converting it all to ethanol. Okay, so that would be the final product. Yes?
I have a question about that.
Okay.
First, how do you know that in the first step, it doesn't do the alkylation? Because isn't it the enolate that forms like a less?
Whoa. Do you see the little one in parentheses?
Yes.
That means that happened on Monday. You see that?
Yeah.
Two? That means that happened on Tuesday. There is no alkylation in step one because the methyl iodide is not there yet.
Okay, so it would preferentially form like the less, because even though it can form an enolate like in the like a tertiary enolate, it won't form that. It'll form this like the less substance.
Where is this going to form it? Where is this going to form an enolate? It
like
one here.
Yeah.
Do anything?
Oh, because it's the first step. That's what you were saying, right?
Yeah.
Okay.
Ones, these twos, these threes. This is not a list of ingredients, right? These are steps. This happens on Monday. The reaction stops here after step one.
Okay.
Now you add the methyl iodide. That's step two. So I don't know if that's what you're asking me, but it can't alkylate in step one because methyl iodide isn't there yet.
Okay, so for example, if you wanted it to alkylate in the first step, you would have to have that base with the haloalkane in like a one step.
Yeah, and that would be a disastrous thing to do.
Okay.
Because how does this guy know that it's supposed to make an enolate. When this guy is also in there, you're going to get a Williamson.
Okay.
So you
Got
would
it.
never have all three of these together.
Yeah, that's what I thought, but okay. That makes sense.
Okay?
Thank you.
Ones of these twos, these are steps. The reaction ends after step one. The reaction ends after step two. The reaction ends after step three. Now you have to keep adding more stuff. So
Okay.
does that help at all?
Yeah, thank you.
Sorry, I have a question.
Okay.
So can you explain why is the third steps there? So why do we need the acid on the third step?
The acid doesn't bring about any new. The acid doesn't bring about any new chemistry. All the acid does is you might have some ETO minus left after step two.
Uh-huh.
Just there. It's not really that important. There's no new chemistry. It's
Okay.
not decarboxylation, right? Because it's not. I don't see any beta keto acids.
Yeah.
So it's just there. It's workup, meaning it's just cleaning up
Okay.
reaction mixture.
Okay, thank you.
Okay, so let's try another one. Okay, maybe. Okay, let's predict the product here. So you want to be able to recognize the reactants, the reaction conditions, and you want to be able to draw the product, obviously. Usually without having to write mechanisms for everything. So what kind of reaction is this? Oh, this is easy, right? Diels-Alder. I see the diene, I see the dienophile. So do you know which one is the diene? Hope so. How about the dienophile? Okay, so let's draw the structure of the product and make sure that we understand all of the stereochemistry and the regiochemistry. Okay, so there's the diene. It has to adopt this S-cis conformation. This double bond is trans, so I have to faithfully translate it here. So of course there's a hydrogen there. It's a trans double bond, so I'm putting OMe over here on the right, and I'm putting hydrogen over here on the left. And this hydrogen is near the front of his tabletop. That's going to be a wedge in the product. Okay, the dienophile is sitting on his own tabletop. But what do we remember about Diels-Alder regiochemistry? The electron withdrawing group on the dienophile and the electron donating group of the diene have to come out 1, 2, or 1, 4, where I'm counting the carbons in the new cyclohexene ring. Okay. So and also remember that the electron withdrawing group of the dienophile has to be tucked under the diene. So how can I make all of that happen on this little tabletop? it's going to be, this is the correct disposition of the dieno file, where the electron withdrawing group got tucked under the diene. You see how this carbon-oxygen double bond is in the back of his little tabletop? That's what I mean by tucking under. Okay, and so now the product. Oh, and also the electron donating group and the electron withdrawing group are going to come out 1, 2. So there's my new double bond over there. This hydrogen is near the front of his tabletop. That's going to be a wedge. And so this methoxy is on a dash. Okay, so this is called a methoxycarbonyl group. It's in the back somewhere. So that's going to be in the back. See how he's on a dash? He's on the back. He's in the back. All right, and now this bond is part of a 6-membered ring in the front. And there's a hydrogen here, right? There's a hydrogen here. And see where he is, he's pointing toward the back of his little tabletop as well, so that that hydrogen comes out here on a dash. Okay, so that would be a fairly ugly drawing of the product. If we wanted to straighten it up, if we wanted to make it look prettier, I don't know how prettier I can make it. That's a big drawing. Try again. Oh, it's Monday. OMe over here. Methoxycarbonyl there. Bomb. Hydrogen on a dash back there. So that would be just a cleaned up drawing. I think on the exam, if you draw something like this, and if it's easy to interpret, if those hexagons are really hexagons and not something that looks like that. Looks are everything. So how'd that go? Yes? Tabletops, tucking under, 1, 2, and 1, 4. So here's the new cyclohexene ring. That's carbon 1, that's carbon 2. So when we talk about the regiochemistry of the Diels-Alder, the pre-existing electron donating group and the pre-existing electron withdrawing group come out 1, 2, or 1, 4. And we're counting the carbons on the new cyclohexene ring. Yes? Okay, so maybe just 1 or 2 more. An easy one. Okay, what's going to happen here? deoxygenation of an amide carbonyl using lithium aluminum hydride. So an amide plus lithium aluminum hydride results in deoxygenation of the amide carbonyl. Okay, so that was easy. All right, just one more. Says here C18H14O. Now, I like to be nice. I'm not nice all the time. But you see this little 2 that I put here? That's a big hint, right? You don't need that 2 because you're not working with one molecule. You go into a lab, you pour out some of this stuff, you're not pouring out one molecule. You're pouring out 10 to the 23rd molecules. So that regardless of whether that 2 is there or not, it's the very same reaction. You're not dealing with one molecule. You're dealing with 10 to the 23rd of them. So what kind of reaction is this? It's an aldol with dehydration. Okay, so how do I know that it's an aldol? Because it's the aldol recipe, something that can enolize. You're going to get enolization here. And then this attacks another aldehyde or ketone. So we have another aldehyde or ketone. Well, it's not really another one. It's really the same one. As I said before, you're dealing with 10 to the 23rd of these molecules, not with one. There's my nucleophile. There's my electrophile. It's the recipe for the aldol. Star and the dot are going to hook up with a new double bond in between. How do I know that the dehydration happened? That's what this formula is telling you. See, right now I see 2 oxygens, but in the product I don't see 2 oxygens, I only see 1. That's your big hint that dehydration, the aldol dehydration occurred. An oxygen is missing. It came out as a molecule of water. The product, my star and my dot hooked up with a new double bond in between. Let's see, don't move this up. All right, so that would be the structure of my product. And I think that must be C18H14O. It's an aldol. Yes? Okay, now let's try some mechanism. All right, so let's write a mechanism for this reaction. So what kind of reaction is this? Well, I see these basic conditions, and I see stuff that can enolize. I see the formation of a new six-membered ring that wasn't there before. This is a Robinson annulation. What's a Robinson? It's a Michael followed by an aldol with dehydration. That's how I see that molecule of water. Also, I noticed that I'm starting out with 2 oxygens here. I only have 1 oxygen there. So that's another clue that it's an aldol dehydration. Okay, first step, enolization of this guy, right? Because we already know it's a Robinson. That means an Michael followed by an aldol. And so this is the alpha beta unsaturated carbonyl. That's the product of the aldol. So first step, OH minus comes in, removes the alpha proton. It's going to remove this one. There's my enolate. And now the enolate attacks the beta carbon of the alpha beta unsaturated carbonyl. That's the Michael stage of this reaction. Now, as far as writing a mechanism is concerned here, oh, and this made water, by the way. As far as writing a mechanism is concerned, you can get really bogged down writing all kinds of resonance structures and stuff. So one thing you could do is push this bond over here and then push this bond over there. You could do that, but that's just a bunch of okay, let's do it. So the negative charge hooks up to the beta carbon. There's my double bond, O minus, bump, bump. Okay, so that was the Michael addition to the beta carbon of the alpha beta unsaturated carbonyl. Okay, and so I see that O minus, and I have water around, I have ethanol around. This is a pretty good base, so this undergoes protonation either by water or by ethanol. It's impossible to tell by which one. So all I'm going to do is maybe something like this. H solvent. I don't know what's protonating that O minus. Could be water, it could be ETOH. Both of them are candidates. So I have that, and so this would, if this is water, I would have OH minus. If this is ethanol, I would have ETO minus. Okay, and what's this? Oh, that's an enol. And what do we know about most enols? They are unstable relative to their keto tautomers. So this thing undergoes a tautomerization. Now, on the exam, I think it's okay if you write tautomerize, or you could go through the steps. I don't think maybe that's what what the graders would be looking for in this mechanism, right? It's all the playing around with the enolate and various other steps. Okay, so we're there now. And notice this was the Michael. What's the product of the Michael? A 1,5-dicarbonyl. Okay, so that's the Michael addition. Now we're ready for the aldol addition. So this guy can enolize. 1, 2, 3, 4, 5, 6. You're going to get a 6-membered ring. if you enolize here, it's going to be a tortured ring system. No good. This guy can enolize here. 1, 2, 3, 4. No good. This guy can enolize here. 1, 2, 3, 4. No good. Enolize here. 1, 2, 3, 4, 5, 6. Yep. And so there's a proton here, and OH minus comes in and removes that proton. So OH minus enolizes this proton. Water is produced. So I've run out of board space, so I'm going to have to continue and conclude up here. And now it's time for, now it's time for the aldol steps, where the enolate attacks the carbonyl. It's an aldol, it's an enolate plus an aldehyde or a ketone. So finally, at last, I can draw a decent 6-membered ring. Bomb, bomb, bomb. Bomb, bomb, bomb. Okay, so now remember, water and ethanol are around. They can function as proton sources. I don't know what functions as a proton source. I could write H2O there. I could write ETO, HOET. Okay, so I'm there now. That's the aldol itself. That's the beta hydroxycarbonyl. This undergoes a dehydration. So once again, there's an alpha position that is enolizable. So OH minus comes in, removes this proton. Dot, dot, minus in the alpha position. And now it's time for the dehydration. These electrons come in here, kick out OH minus. And that brings our mechanism to a close with the production of this alpha beta unsaturated carbon. Yes? Any discussion about this mechanism? Okay. All right, so let's try writing a mechanism here. Whoa, it looks like an optical illusion, does it not? It looks like this thing kind of flipped over, did a pancake flip, right? A mechanism. So what kind of reaction is this going to be? It's an acyl substitution. I see a carbonyl-carbon bonded to something that's not carbon, not hydrogen. That thing that's not carbon, not hydrogen is going to take off. The nucleophile minus a proton, we're under acidic conditions here, is going to take the place of the leaving. Now, I think the most popular thing to do here, which would be wrong, would be to possibly protonate this oxygen as the first step and let this thing depart as a free swimming entity. No good. Because when we see a carbonyl compound, acidic conditions, we have a thematic mechanistic opening, which is we protonate the carbonyl oxygen and then we attack the carbonyl carbon with a nucleophile. So first step, protonation of the carbonyl oxygen. Now what? Attack the carbonyl carbon with the nucleophile. And the nucleophile is this nitrogen. When I hook this nitrogen up to this carbonyl, I'm going to get a 5-membered ring. Oh, that's thermodynamically reasonable. So no, I don't have a free swimming OH, CH2, CH2, NH2. So I have that. And now there's a lot of fiddling and diddling with protons. Just to save time, I'm going to write plus minus H plus, meaning a deprotonation, reprotonation step. I'm going to take a proton away from this nitrogen. And where am I going to bring that proton back? Up here? Oh no. Over there, because now this oxygen has to function as the leaving, right? It's acyl substitution. Now that oxygen can depart. CH2CH2OH, and then a final deprotonation leading to the product. So it's just the implementation of that theme that we've seen oh so frequently before. Protonate the carbonyl oxygen, attack the carbonyl carbon with a nucleophile. That's usually what happens under acidic conditions. Okay. So let's finish up with some synthesis. Any discussion about this?
Is it possible for the ester, like for another equivalent of that starting material to come in and attack the protonated carbonyl?
To attack the protonated carbonyl? Well, you know, it's not likely because what you're proposing is an intermolecular reaction. Molecules have to find each other in the reaction mixture. That is much slower than the actual mechanism, which is intramolecular. This molecule doesn't have to swim around in the solution looking for something to react with. The nucleophile and the electrophile are on the same molecule. This is just going to be so much faster than if a second molecule comes in.
Got you. Thank you.
All right, so let's finish up with some synthesis. C7H12O2 non-cyclic reacts with diethylmalonate. The target molecule is this. Okay, so give me the structure of this guy, and then using this and anything else, come up with a synthesis for that compound. So this plus anything else that is required, and synthesize that alpha, beta, gamma, delta keto acid. Big clue here is the use of this diethylmalonate. We know that that's a highly nucleophilic carbon. So that's going to be a nucleophile somewhere. Where is he in the target? Well, he's probably here. That's an alpha position. That's an alpha position. And maybe we recognize that a decarboxylation happens somewhere along the line. Because I see 1, 2, 3, 4, 5 oxygens here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 oxygens here. Here I see only 3. So some oxygen is missing. Okay, so trying this retrosynthetically, my strategy would be here's my target. This guy here, activate. And remember that this ethoxycarbonyl group is disposable, right? I can make get rid of this by hydrolysis and decarboxylation of a beta keto acid. So right in here, I see, oh, there's my diethylmalonate. This is a 1, 2, 3, 4, 5, 1, 5 dicarbonyl. That means it's a Michael. that's that, right? The nucleophile of my star attack the beta carbon of the alpha beta unsaturated carbonyl. And this guy is an alpha beta unsaturated carbonyl. This is the product of an aldol, where the alpha carbon was the attacking nucleophile and the beta carbon used to be a carbonyl carbon. And now when I look at this guy here, I see he's 1, 2, 3, 4, 5, 6, 7. Yep. He's H12. Yep. And he's O2. Yep. And he's not cyclic. So this would be the starting material. Okay, so there's my strategy. I'm ready to write my synthesis. KOH, H2O, and heat is going to take me, that's going to be the aldol stage. Okay, and so now I take this guy and treat him with ethoxide and ethanol. That's going to enolize the star. I'm going to call this guy Roman 1, right? That happened back at the ranch. So now I have this. I add Roman 1 to him. I'm going to need ethanol as the solvent. And so now I get this guy. All right, and now all that remains is to hydrolyze the ester and to decarboxyl. H3O plus, heat, and there's my target. I get that decarboxylation, hydrolysis, and then decarboxylation. Okay, well, that's all the time we have now because I have to go to another Zoom. Any questions about this?
I have a quick question.
Okay.
How do we ensure that with the decarboxylation step, only one of the ester portions will leave?
Oh, because you get this, right? That's the hydrolysis.
Right.
This is a beta keto acid. And so
Okay.
this goes away, and when that goes away, do you have a beta keto acid left?
No.
So the decarboxylation comes to an end.
Okay, awesome. Thank you.
Okay. All right, guys. So I'll see you next time. Until then. Yeah, you're welcome, everybody. My pleasure.